Hello, 1, 2. Yeah, it's working. Perfect. Sorry for the slight delay. We got everything sorted. So thanks for coming to the session. My name is Bill Tilgiridis. I lead data science for Unilever in Europe. And today I'm going to be discussing how my team is working on improving the forecasting capabilities of our European business through the use of predictive machine learning. We're just going to be talking about, obviously, first of all, the background and providing some context in terms of what we're trying to solve for. I'm then going to go into the solution, providing an overview of what we have been developing. I'm going to touch on some of the key enablers for sustainable maintenance that we have been putting in place for our forecasting solutions. Then some key learnings from a business and from a technical perspective. And I'm going to finish off with some Q&A. So forecasting, as many of you might know, it is tricky business, right? So let's take Unilever as an example. And I've realized pretty late that I haven't put a slide on for Unilever, but for anyone that doesn't know what Unilever is, it's one of the biggest consumer goods companies in the world. We sell our products to what we estimate is 3.4 billion consumers that use it daily across 190 countries. And the portfolio of the products is quite varied. We have from shampoos to mayonnaise to laundry detergent. So Unilever as a business operates in environments that are quite intricate, highly complex. Oops. And are influenced by a lot of different factors, right? So market trends, economic conditions and changes in the consumer behavior. And what is quite difficult, right, is we need to individually predict each of these factors and also how they interact with each other. On top of that, we have, as you well know, unexpected events or events that are difficult to predict. We had the pandemic. You might remember that. It's not too long ago. We have regulatory changes in countries. We have supply chain shortages and disruptions, inflationary cycles. We're coming off one right now as we speak in Europe. And so all of these can significantly impact the accuracy of the forecasts, while also how forecasts can adapt to these changes is challenging to figure out by itself. I want to provide some examples of the forecasts that we're looking on in Unilever as a typical CPG company. So on the left-hand side, you will see what we have, what we call as internal forecasts. And these really focus on our P&L as a company. Demand volume is the backbone of our supply chain planning. So how much of what products will our factories produce, driven from the demand from our customers. Trade investment is quite an important bucket of spend for us, and it is how much we're expected to spend to run our promotions, place our products in optimal shelf spaces, run our in-store marketing activities, provide different customer incentives. Supply chain costs, of course, so how much are we spending to produce and to distribute our products. And there are other forecasts that I've not included there. Media spend is another important factor. So you probably all have seen a Unilever ad at some point in time, either on the TV or out on the streets or on your phone. On the other side, we have our external forecast. So there, we're focusing on what's happening in the market. As I mentioned, we play across a number of different categories, and we sell our products to customers. So we want to understand how these categories are growing, but also how our customers are growing. Pricing growth, as well, is a very important one important forecast to us. And then share. So how much share would we expect to have? It's a key measure of our competitiveness. There are a couple of key important factors. Forecasts need to be available at different levels of granularity. And that is really dependent on the use case, right? I've got in the middle there, you can see some of the typical levels of granularity on the product side and on the customer side. A use case like demand forecast planning would typically be done at a low level of granularity, so SKU customer. For Europe, we are talking about north of 5 million different combinations of SKU and customers for that. On the other side, where we have a market growth forecast that would typically be done at a subcategory customer level, so quite higher up, wouldn't need that same level of granularity. This is also dictated by two things, right? It's also dictated by the accuracy and also by the availability of the data. The second point is that the forecasts are not independent of each other. There are dependencies across the board. And in an ideal world, we would want the development of these forecasts to be underpinned by a common framework and a common set of assumptions. But in practice, this is hard because we have different people in different teams looking after generating different forecasts. There are two main approaches to forecasting. One would be the manual or the expert forecasts, as others they're a lot of times called. The other, the more automated approach. This is driven by machine learning models, deep learning models, statistical methodologies. If they work, well, why not? I mean, and also combinations of those different models. The challenges that each of these approaches have are different. So from a manual perspective, the forecasts are very expensive to generate at scale. It's also very expensive to refresh them on a frequent basis. We have the issue around the inconsistent set of assumptions, which I touched on just earlier. And there's also the aspect of the human bias that can affect accuracy. On the other side, with the automated forecasts, we have issues around the historical data availability. So what data do we have to drive the forecasting? We have forecast dependencies. Our forecast outputs are going to be as good as our input projections. And if those input projections are not good, then we will end up with compounding errors. The solution maintenance, of course, so it's all good and great if you produce your forecast at a certain point in time, you evaluate it, it's providing you with an acceptable accuracy, but then obviously you need to monitor its accuracy and you need to intervene when things are not as well performing. And final thing is around explainability. There needs to be an element of trust for the forecasts, which is of course created by demonstrating the accuracy, but also the explainability of the predictions. Being able to understand what drives the output of an automated solution has to do with its transparency, and we know that's a big topic around AI in general. This is the environment that we're operating in and the key challenges. I want to flip this and look at the requirements we have from a technical perspective to enable us as a data science team to develop forecasting solutions that can address these points. So first, we want to be able to experiment in a straightforward and time-efficient way. The time to value is critical. And reaching the first milestones, let's say in the form of a proof of concept for our project, is key to make the decisions whether to further invest on the project or whether we want to stop there. The second thing is we want to have well-defined and established deployment processes for our products. This relates to both code and the models themselves. So from the code perspective, this is about having a way to manage the code, having a way to test the code in the form of unit tests or integration tests. And from a modeling perspective, it's about tracking that performance and being able to extend the decisions on model selection or model deployment on that performance. And finally, we want to be able to sustainably maintain our solutions. We don't have infinite resource and capacity as a team, quite the contrary, actually. So as a team, we want to be able to have a balance between adding new features, working or exploring new capabilities, and maintaining the existing solutions. And obviously, the more stuff that we're putting in production, the more stuff that is live, the more stuff that we need to maintain. Now, what have we been putting in place to tackle the problem is a reusable framework for predictive machine learning, underpinned by a set of libraries that deal with the different stages of that machine learning lifecycle. The framework is there on the screen. I'll touch on each of the different modules in a little bit more detail. I do want to call out one major point is that we want to have a repeatable process with which we can approach each of the different forecasting use cases. And that process uses the same set of tools that drive the output. That does not mean that we want to apply the same exact data transformations or the same feature engineering, same feature selection or models to each forecasting use case, but we want to be able to select all of these from the same framework. And this is important to avoid the duplication in terms of the development, while we're also applying a layer of governance in terms of how that development happens across the data science team. And we also simplify the maintenance of the forecasting solutions, given they all use the same engine, which is this framework. Let's go into the first module, which is around the data preprocessing, and that focuses on the data transformations, the feature selection, and the feature engineering. If you look at the top there on the code snippet, we initialize an object of the main class of the library called preprocessing. Takes as inputs the targets and the holdout period that we run our evaluation on, which is also typically the forecasting horizon. Following that, we have a set of methods that we apply. And these are things that are probably quite well known. So we have one-hot encoding, power transformations. There's a more extensive list on the table there of the different things that we have available, the different transformations. Following that, we have another method that is applied for feature selection based on Shapley values. And from there, we structure the time series data in a way that can be used as an input for the model. That's achieved through the prep ahead method. And final step is that we construct a scikit-learn pipeline to record all of the steps that we take along the way. Moving to the model training phase, we have two libraries there that we use. First is the machine learning regression library. There we use models, machine learning algorithms such as XGBoost, gradient boosting trees, random forest, again, all from the scikit-learn library. And what we have there again is we initialize a reg forecast object that takes as an input the target. The model list is the list of models that we want to train in our specific use case, the forecasting horizon, and some other parameters that need to be configured, the path for the MLflow experiments, for instance. The logic of the library is presented in the diagram. So we select the first model from that model list. We then run the hyperparameter tuning. We use a library called HyperOpt to achieve that in a more automated way. And then we evaluate each of these runs based on the loss function. Selecting the loss function is a method of the class. Set loss function is one of the lines there in the code. And then obviously we run then the HyperOpt runs until we have reached that maximum number of iterations. After that, we have the optimal hyperparameter chosen, and we run the walk-forward validation to be able to give us the accuracy or the error of the run. Following that, we log all of the metrics and the model to MLflow, and then we repeat the same process again for the next model in line. The second library for training is a time series forecasting library, and that is in principle, really use the same principles actually as the regression library, but it focuses on the more statistical methods such as your Saramax, Hughes, STL models. We have Profit as well included there. Again, same principles here. We use hyperopt parameter tuning. We also use walk-forward validation. The way we have it separate at the moment is because it's a different structure of the time series data is needed for these models. Hopefully, further down the line, we can converge into one modeling library. The one thing I want to mention is the walk-forward validation, which is part of those libraries and is the recommended form of validation to apply for our models, respecting the time series nature of the data. To quickly summarize the difference for anyone that might not know about walk-forward validation and its difference versus a methodology like K-fold CV, which is quite popular. So we obviously still have split the data to a train and a test set, but the rule here is that any observations that form the train set occur before the observations of the test set. Thus, no future observations can be used in constructing the forecast. We repeat this process, so there is that kind of sliding window until we have used up all of the available observations, and then we calculate the forecast accuracy across all of the different test sets. And this process can be applied for multiple forecasting horizons, one-step, multi-step, and you can also use the latest data that you have available for your evaluation, which is often the case more representative. It should be more representative, at least for your short-term future data. And the other thing that is important to note as well is that it's important to choose a validation period over which your test windows will run that covers important seasonality effects, forecast cycles, so you ensure you validate your model's performance in those instances. The next module focuses on deployment of the best performing models to production, and that happens by MLflow. The process here is quite straightforward. We will load all the models that we trained and registered, which would be assigned stage none in the beginning. We then compare the models based on selected error metric and then promote the best performing model to staging. Once we're there, there's an additional check, and that is if there is a model already in production, then we again compare the error with a model that is in production. If the error of the staging model is better, then we would archive the model in production, and then we will get ready to promote the new model to prod. If the error is worse, then we'll just keep whatever we have in production and then archive what is in staging. It is recommended to also have an additional test before promoting the model gets deployed, such as ensuring that the new model's predictions on a standard validation set meet a fixed threshold of quality. Moving to inference, here we simply load the models, run the predictions with some additional tests on its quality, and we have also an option to run Bootstrap, which essentially will give us an interval, a prediction interval. And again, it is recommended to have a prediction interval when providing a forecast to just provide a view of the uncertainty of the model. The way we do that through bootstrapping is essentially we randomly sample with replacement the model's residuals and add these to the predictions. We repeat the process a number of times and then take the percentiles of choice from the bootstrap list of predictions to create that lower and upper prediction bound. The last module focuses on explainability so that we can understand some of the inner workings of our models. It was important for us to select a methodology that can surface those feature importances in a way that our end users could easily interpret them. The SHAP library fits the bill quite nicely, given it's model agnostic, so we can actually use it across all of the models in our machine learning library. Stands for Shapley Additive Explanations, and is based on Shapley values, a concept from game theory. For anyone that's not aware of it, so each player or each feature, in our case, is assigned an importance value based on its contribution, and that is measured by the difference of the outcome, whether we include or exclude the feature from the model. And the last thing that is important also, that it enables both global and local interpretability. By local, it means that we offer a breakdown of individual predictions to the contributions of the features. And also, we can have a global understanding then if we combine many local explanations of each prediction to have an understanding of the global model structure. So it is quite handy in both kind of like those two different scenarios. That's the framework that we put in place in the different modules that are part of it. The next thing I would like to share is some of the key enablers for sustainable maintenance that we've picked up along the way while we have been developing our solutions, and have also become part of our framework. The first one is modularization of our code. The organization of the code in library classes and functions that I've just described really kind of make part of it. This is important for a few different reasons. It's important for managing dependencies and refactoring code when that is needed. And it's also a key enabler for our testing. So essentially, we have one engine based on which our solutions are run, and we're focusing on maintaining that one instead of many. The next point is around parallelization. We have been developing our framework, as you saw, in Python, but we need a way to run this at scale and benefit from using Spark. So applying pandas has become our good friend there, and it is valuable to get the most out of running our code in the Databricks platform. Parameterization using config files is also important to manage all of the dependencies and the important details, of a project in one place. It would include the inputs, the outputs, any parameters that are important for the modeling. This enables us to run our machine learning code using pipelines in a straightforward and painless manner. Code management and testing. I mentioned that earlier on. We want to have those well-defined and established processes, and we have code deployment and model deployment, and both of these feed in our main machine learning pipeline, from model testing all the way to the monitoring. And finally, speaking about monitoring, what are we going to monitor? We're going to monitor two different things, the data inputs and the model's performance. First, on the data inputs, what we care about is the quality, the completeness of the data type consistency, outliers. From a drift perspective, right, we want to look at whether there are changes in the distribution of the data, or any changes in terms of the trend, so the seasonal effects. From a model performance, obviously the prediction accuracy. So we want to look at the accuracy of the live predictions, and we want to compare that with the accuracy of our evaluation set and see how far off we are from that. The bias, whether we're systematically over or under forecasting, is something that is also important to know if there are any changes there. And finally, changes in feature performance, in feature importance. Again, something that could hint towards an issue, something that we need to look at. And I want to close this presentation by sharing some of the key learnings that we have picked up as a team over this journey that we have been on with building predictive ML tooling. I've got 6, I think, learnings in total. So I've tried to group them in business and technical, although the line is, I think, a little bit thin. From a business learning perspective, first, it goes without saying, I think, that we need to measure improvements versus an existing business process to showcase the tangible value that our project is driving. Of course, this can be as straightforward as the accuracy. If you have the accuracy of the business process from before, if it was a manual forecast, for instance, fantastic. A lot of the times, though, this is not really available. So in that case, you can agree with your business stakeholder on a specific benchmark, right? Always have a good benchmark to beat. Then there are other ways to showcase the value if, let's say, you don't really see a lot of improvements in terms of the accuracy. We can talk about how an automated forecast versus a manual forecast saves a lot of time and effort. So you can show the impact in that way. Working towards a transparent and explainable solution. So again, here we can't assume that everyone works back the new way of working, right? So the new forecasting process without understanding anything about how it works. They will need evidence, and the trust will need to be created, and they will need to have answers around kind of like the whys and the hows. This is key, especially in the beginning, based on our experience. So as once that confidence or that trust has been built, then it is easier to move, let's say, to less explainable but more accurate solutions. But again, I think transparency is always a point that will be raised in terms of the AI models. The last point here is investing more time in understanding the business requirements. It is really important to work together with a small stakeholder team to fully scope out the project, to agree on what success looks like, and those milestones, right, in terms of like what is the POC, what is the MVP, what are the future stages of the project. So engagement is very key, especially for those, I think, more challenging projects in the data analytics world. From a technical perspective, again, always have a technical benchmark in this case to beat. So you're making sure that you're not spending time on something that is not really adding value. For instance, from our repeatable framework that we have built, we have been able to reduce our POC completion time by almost 50%. And that is significant, right? I mean, time to value is something that we get grilled on a lot of times as a data science team. How can you do this better? How can you do this faster? So where we can cut back on that time is great. The second thing is to build for change and to have kind of like always that maintenance hat on. So how this works really in the beginning is that you work on your POC, and then deadline after deadline, and you suddenly have your POC code in production, and it's just unmaintainable. So a framework, again, like the one proposed, will help you to reuse what you effectively have available, and then you're just contributing to each use case as you go improving the framework. And the last point I wanted to make is around evaluating requirements against the effort and the cost. We need to provide a transparent view on the effort and the cost and the time that it takes to meet certain requirements from our business folks. We always need to be able to challenge based on the ROI, and we need to have a voice on the table, right? So we need to make sure that we act as the owner of the technical solution we're building, and we are happy to challenge some of the points raised. That's the presentation. Thank you very much for listening.